Okay. Wait. Good morning. Hold on. Sorry. Once. Good morning. Thank you. Good morning. One sec. Okay. The recording was not, but it is now. Okay. Good morning. Good morning. Good morning, Sydney. Good morning, Loani. Good morning, DJ. Good morning, Kayla. Good morning, Sarah. Hold on. I'm looking in the chat. Thank you, Kayla. Awesome for the double. Chat. Wait. So Loani, sorry, Ashley, good morning. I saw you before. Loani, good morning. Thank double. Maya, good morning. DJ, good morning. Thank you for the double. Pushpita, good morning. Lena, good morning. Sydney, good morning. Double. Kayla, good morning. Double. Thank you. Good morning, Sarah. Thank you for the double. Good morning, Erica. Sorry, I missed you. Good morning. Thank you for the double. Okay. So we're gonna start in a second. Are we gonna start in a second? We're gonna start in a second, but I'm still a little confused about something. Um, um, oh, okay. I see that. Okay. Oh, I see that. Okay. Okay. I'm just making sure that we're on the same page about. So do I see Haley or Duran or oh. Um, I see the question in the chat. Give me a second. That's a legitimate question. I'm just Zoom got updated is partly what's confusing me, but also I'm just making sure we're on the. So Isabel, Haley, Duran, Stacy. Isabel, Duran, Stacy, Haley. If you hear me, if you're here, maybe send me a private chat. I'm not trying to. Isabel, Haley, Duran, Stacy. Yeah, if you hear me, send me a private chat. If not, okay. Erica. No, I see you. I see. Okay. One last thing. I see a private chat question. I want to not use a person's name, but I want to answer the question, but I think I want to make sure I have the correct answer to the question. Okay.
Professor, can I ask a question?
Give me one. Yes, but give me 1 second, please, because I'm trying to. There's a question in the chat that I'm like trying to make sure I have the correct answer to. So 1 second. Sorry. Oh.
Okay.
Oh wait. Oh, I see what happened. I see what happened. Hold on 1 second. Um, okay. Wait. Yeah. So I'm gonna answer that your question in 1 second. Was that Alice or I think it was Alice or who? I'll answer your question one. But first, there's a question in the chat about homework. it threw me because I thought I had already. So apparently I made a mistake in the. So there's a question in the chat about homework 6, whether to be pushed back or not. And I actually thought I had already done that, or I thought I had made a deliberate adjustment, or but I did a typo, so I see why there's confusion. So the answer about homework six would have been due um, a week from today. It will instead be due a week from this Thursday. And the truth is, as soon as we get rolling here today, mostly what we're going to be doing today and then in your lab is wait, your lab is Thursday. Right. Well, mostly what we're going to be doing today is helping you, is setting up that homework. We're going to be doing, or at least we're getting you, we're helping you with it. So homework 6 should be okay. It's now due a week from this Thursday. I mean, we can only, adjust things so much because we have to keep going with all the material and everything. And yes, I'm going to get you in 1 second. But then the other quick thing before I forget, or just to clarify, there's a homework 5A and a homework 5B, but what you will notice is that there's no deadline at all for them. They are optional anyway. I mean, all homework technically is optional, but they're even more, they're like extra credit. And and we're sort of, so what I mean by that is that I never even sort of pretend or promise to go over them in class. They are for points if you want them. I mean, they help, but we don't directly deal with them in class. I'm talking about homework 5A and B right now. And also, let me be super clear. So you can do them or not at your will when you have a chance. Or you could choose one, and not do the other. Specifically, the reason they're packaged together, 5A and 5B, is because one of them, I believe it's 5B, the one that's called tone. That one is particularly for those of you who might be eventually taking the MCATs. That is a set of exercises that of extensions and applications of this material that are really not crucial for the class, but that do come up on the MCATs. So, and I could talk to you privately about that if you want, or at another time. But so don't worry about homework 5A or B is the first thing I'm saying. Second thing I'm saying is 6 is what I'm going to start dealing with directly in a moment. But that will be, and that is due a week from this Thursday. Okay, Alice, question. Yes.
Yeah, so I had a question since there was a few of us that um met up like over the weekend. Like we had a Zoom session on our like own time outside of class that I recorded because I wasn't sure if we could submit that for credit. So I wanted to ask if like we can or if that doesn't count towards the credit for the course.
Oh no, that's awesome. Oh, I'm sorry. Yeah, no, that's great. You could definitely you should. Yes, you should submit it, and they should too. If nothing else,
Well, I
it,
recorded the entire session, so in like 40-minute periods because Zoom for students like for free is like in 40-minute intervals. And then it just like kicks you out of the meeting. So we had a meeting to go to like try and do the midterm together. Um, so I wanted to like see if that was possible to submit for credit.
right. So I'm saying yes, that's great. You definitely can, and they can too. Yes, that'd be great. And if there's plenty of portals where I could see how it would be applicable, but if nothing else, submit it to the multiplayer co-op portal. But yes, that's great. That I appreciate that absolutely, and they can or should as well. If anybody who's involved, I think that's terrific. Thank you. Yes. Um. So yeah, yeah. Um. I won't. Well, anyway, yeah, I'll leave it at that. If there's further things to discuss about it afterwards, we certainly can. But yeah, I think that's terrific. No, and I gather, all right, so I gather from various sources that people in various combinations or various modalities have been working together, and that's terrific. Like that's what we want. Like the more of that, the better. And I'm looking. Okay, great. Wait, I'm looking at the. right. And if you have whiteboards or anything to submit from any of that, yes, please, yes, I think it's great. It is part of the hope and objective of this kinds of exams that we do, that it does motivate people to get together and work together. I can't praise that enough or thank you enough. And so, and yes, and maybe at some point I'll make a separate portal just for stuff like that. But unless I don't, or until I do, you put it in like at the multiplayer co-op portal, for example. And yes, whiteboards, sure. The reason I'm not dwelling on it for many minutes right now, I also want to be like I have different feelings and different opinions at different times about, especially when it's videos and stuff. I mean, the whiteboard's definitely the thing. What I'm trying to say is, I try generally to resist the temptation to watch them, even when people send them to me so that I can post and distribute them to the rest of you, which I'm delighted to do. Like if it makes it easier for me to, give access. But I try, unless I'm told otherwise, I try not to watch them because I think there's like a privacy thing. I don't mean a legal privacy thing, but I think that part of the virtue for some of you guys when you get together is what can be accomplished when you don't think that I'm judging you, or honestly, or like that I'm not involved in the particularities of what you're saying. I mean, yes, I'm delighted to give credit for the fact of you doing it. So, all the yes, but I'm just trying to explain in a way, and I'll move on, why I don't necessarily scrutinize them or get too involved in details, because I think for some of you, you do better. They work better for you if you know that you're sort of protected from me when you do it. Anyway, we can have that discussion at another time, or you could privately talk to me about that. But just so you know, that's why I don't. That's my feeling, is that I couldn't have gotten through my undergraduate physics major or the 2 times I went to graduate school. I literally could not have gotten through if I did not have peer groups where we felt like we could then go away and try to sort through all this stuff in a manner where we just didn't care what the professor thought of what we were doing, or that we didn't think they cared. There's something to that. So anyway, so thank you. Okay, and bottom line but yes, distribute them, send them. I mean, yes, or whatever. And then of course that gets us to, and I do want to move on. Most of you, except for a couple of you, thank you for acknowledging the update I sent to you. I mean, I think we're all here. I think every one of us in the room, I believe we all understand that the deadline for the exam has been postponed, and so you're still working on it, which, by the way, also sidebar, thank you for being here in the middle of that. Like, I hope the extra bonus time is helping you all, but I also know it's like stressful to sit in a class in the middle of while you're still working on the exam. I get that, but that's like a compromise that we're making, because we do have to we have to move on with the class. But I appreciate that you're here, and I appreciate that by and large, most of you sent back the thing that confirmed your understanding of the new arrangement for the exam. And yes, to be explicit, I think this is understood, but why you're getting that extension is in large part because of the sense that was given to me that people were working hard, responsibly, in groups, and sort of recognize the kind of standard of quality that I was looking for. And apparently people thought that it might even be within reason, just with a little extra time. Uh, Basically, it's because representatives came to me from what appeared to be larger groups of students that I took this so seriously. So, I mean, that's all a compliment and a thanks. Like, I feel like we're all trying to recalibrate this class or class morale, and I'm very interested in doing that. So, yes, I'm hoping this whole thing helps. I'm hoping the quality of the work will be very good. And I'm hoping that you'll all benefit enormously from having helped each other, but that you'll still, in the final document, show me that each of you as an individual gets what's going on. Like that is the fine, tricky line I'm asking everybody to walk. So, okay, a little, but it is a fine, tricky line. Okay, all that said, I'm now so, and I'll be, we'll say more about the exam and all that, once it's in and once we get it back. Um, wait, is this recording? Wait, what? Okay. It is recording, right? It is recording. Okay. So now you have to bear with me, and I have to shift gears to an entirely new topic. The good news, we're moving on with the material. Of course, it's a related topic. I mean, there's a reason this topic that is also part of this course, but it is an entirely new topic. I'm going to tell you right now everything I'm going to say today about this new topic. One is meant to help you with the next board meeting that you're going to have in lab. I'm not sure if it's going to be this week or next week, but you're going to have and you may never have, oh, well, you haven't had a board meeting this semester, I don't think. So the lab that's going to introduce this next topic will be like a problem solving session. I want to prepare you for that right now. That problem solving session will be motivated by the homework sheet that is due next week. So everything I'm going to say here is to help with the lab, and the homework sheet. And although it is a new topic, I'm going to turn the page in a second and get going. It shouldn't be, it may be a clean slate opportunity for many of you. We're not going to get too abstract with it this week. I recognize that you're all running on, half tanks, and distracted. I recognize that. And so am I for other reasons. I recognize that. So I'm going to tell you right now, if you bear with me, if you take notes, if you try to sort of like relax your mind or set aside other concerns right now, this won't be as crazy complicated as something yet, as something sometimes are in physics. And it's not going to involve calculus. I'll say that. What I'm about to do does not involve calculus. The math is not abstract for the most part. Okay, so okay. Oh, you've had a board meeting. I'm sorry. Oh, you did have a board. Oh, that's right. You've had a board meeting. I forgot. Yeah, that's right. All right. But you're gonna have a different board meeting now, on a new topic. Yeah, thank you for reminding me. Right. Okay. Oh, okay. Wait. Oh, okay. And thank you for the direct. I'm seeing all the direct ties. Okay, and thank you. Well, and by the way, all the people that are correcting me in the chat about the board meeting, I appreciate that. First of all, it shows you're paying attention. Second of all, remember there's a portal for that. Respectfully corrected. You submit like you just. I appreciate that you corrected me and that you did it respectfully. Like seriously. So, I'm now going to start. I hope where to go. It should come. Hello. Yes. Okay. This is today. This is today. Yes. Okay. So these numbers are not numbers you have to memorize. These are numbers that I'm going to give you by the end of today. You're going to use them in the upcoming stuff. The topic that we're getting into now, is electrostatic forces chart, excuse me, electrostatic charge, electrostatic force, electrostatic field, and electrical currents. Electricity is what we're about to get into, okay? Quick, well, I'll just say that we're about to get into electricity. However, in order to get into electricity, oddly, we have to take a step back and either tell ourselves or remind ourselves, depending on who you are and what you did last semester, we have to either tell ourselves for the first time or remind ourselves some things about gravity. It turns out that electricity works very similarly in many huge respects. It's very similar to the way gravity works. So the way we understand electricity, we first remind ourselves about gravity. Specifically the aspect of gravity. So what this says is we're going to a new unthingy topic here. The topic the reason it fits into this course is because the topic we're getting into is often known as action at a distance. We're going to transit. So what the board says right here is we're going to do some background on the universal gravitational force and transition from that background today into the universal electrostatic force. Both forces have a very unthingy quality to them that I'll ask you to sort of look out for as I'm talking today. You'll see what I mean by unthingy and therefore why they are part of physics 204, as we go. Okay, so it's about gravity right now. Um, so Newton, and again, some of you may know some of this from last semester or from high school, but some of you might not. Again, I'm not making, so maybe for some, so it might be helpful if you have a little bit of a background in this, but I want to make it very clear right now, even if you don't, it's fine. I'm not making that assumption. I'm starting from scratch here. Um, uh, I'm starting from scratch. So, Newton's law of universal gravitation is about what any one little bit of mass automatically and always does to any and every other little bit of mass. So the given that we're talking about, the assumption is, say you have a point mass called M1 somewhere over here, somewhere in the world, over here, in the lab, in the universe, in outer space, wherever, a bit of a point mass called M1 over here. And then you have another point mass called M2 over here, separated by a displacement called R vector. Now, first of all, to be clear, when I say point mass, what I mean is some amount of kilograms. M1 could be some big amount of kilograms. M2 could be some smaller amount of kilograms. It's an amount of kilograms, but it's called a point because the belief is that these kilograms have been compressed or shrunk or chopped or something to some tiny, tiny, say, nearly infinitesimal volume. So it's a point mass because it's got a huge magnitude of mass, kilograms, but it does not take up really any noticeable or measurable amount of space. High mass, low volume. And the mass could be anything, any number of kilograms. So we got a mass one over here. Often the capital M1 is often referring to what is the bigger of the two masses. And then we've got M2 over here. And they're separated by a displacement vector R. Now I'm going to remind you a couple things about vectors now, not calculus, but vectors. And I'm even going to tell you that you sort of do need to, well, you do need to remember or understand what I'm about to say in order to do the homework. You don't necessarily need or understand what I'm about to say to do at least the beginning of the board meeting in lab, but you will need it for the homework. What is that? That is that R vector, remember, by definition, any vector has size and direction. These days, we package the size and direction into one mathematical package, a monomial, for a product for which R, written without any symbol above it, just R itself is the raw size, the scalar amount of the vector. So in this case, if R with an arrow over it means displacement vector, then R with nothing above it means the distance of that displacement, right? And then R hat, R with the caret over it, refers to the raw direction of the vector. So we view the vector as a raw size times a raw direction. Like the R hat is a unit vector that by definition has a size of 1, but points in a particular direction, the direction of R. So R, the entire vector, is the product of its raw size times its raw direction put one last final way before I go. And this is like, just like a review of like vector stuff that we were saying a couple weeks ago. Put one final way. It's a reminder that whenever you think of a vector, one way you might think of it is sort of read it right to left. Think of any random vector as first a unit vector, a vector of size 1 pointing in a certain direction. And then, so an arrow of size 1 pointing in a certain direction, and then you take that arrow and you scale it, you stretch it up or you shrink it down by a certain amount, the amount being its name without any symbol above it. So the whole entire arrow of R is really R hat stretched or shrunk by the amount R. That's how we think of building arrows of random direction and size. Is we build an arrow of a certain direction and then we stretch it to a certain size. Just a way of thinking of these vectors. So we have a point mass 1. This is just the given situation. We have a point mass 1 over here, and then a displacement, that arrow that points from M1 to this other mass M2. What Newton says is if you have that situation, if you just have one mass and then separated in space from another mass, automatically the first mass will exert a force onto the second mass. This is what Newton says. This is what the law of gravity says. That any mass over here will automatically always be exerting a force onto any and other. Okay, wait. Okay, 1 second. All right, I'll just finish the sentence. So any one mass, 1, will automatically exert a force onto any other mass, 2, that's some certain displacement away from it. Now, wait, so in the direct chat, yeah, I'm saying, wait. Okay, so so I'm about to show an example with numbers. Actually, I mean, good question, but yeah, I'm good. But I haven't actually said anything yet. That's a problem. I'm taking too long to say like nothing. R hat. Wait, but what I am saying this: R hat is the unit vector for R. Like for vectors in general, for any vector R, what R hat is by definition is the entire vector. Is the entire vector divided by its own length. What I'm saying is a letter with a caret over it means a vector that points in a certain direction, but necessarily by definition has a length of 1. So it's a unit vector. It's a vector that has a size of 1, but points in a certain direction. The purpose of it is to show you the direction of the vector, as opposed to the R with nothing written above it, just shows you the size of the vector. So I'm saying in general, I am going to do an example with numbers in a second, except this part is just like old new. Like this isn't new. This part about vectors. I'm just saying any given vector is the product of its direction with its size. That's what I'm saying about that. Oh, okay, cool. Okay, and as far as how gravity works, I am going to do an example with numbers in a sec. Wait, that so I'm looking at the chat. The unit vector, any vector can point in any direction. That's the point of a vector. It can point in any direction. I mean, you could say positive or negative. Sure, if you're in 1 dimension, if you're in 2 dimensions, it could point in any direction, like any theta, any angle at all. And since any vector could point in any direction, then yes, any unit vector can point in any direction. The unit vector for a given vector points in the direction of that vector, but what makes it unit is that it specifically only has a size of 1. I mean, these are good questions, but the only reason I'm worried about, I have a little worry that you guys are worried that I may be saying too much about just the background of this. Like, you might be thinking it's a bigger issue than it is. So let me go on for a second and just try to get to the gravity piece. Wait, but you have seen, wait, we totally did this. Hang on a second. Wait, didn't we totally do unit vectors 2 weeks ago? wait a second. You didn't we do the whole thing with I, J, and K? I'm not trying to be weird, but um, yeah.
Yeah, we did.
Okay. Okay. All right. Thank you. Yeah. So and don't get me wrong. Okay. So let me go on for a second because yeah. Okay. I'll just go on. But the main focus that I'm assuming we sort of understand that, but my main focus is this claim about gravity, which here it comes. Um, well, okay, but yeah, but that doesn't mean you've never seen it before. But okay, wait. Okay. I see what you're saying. Oh, okay, all right. Let's just like time. I mean, do over. Let me just. I think we're all a little stressed right now, so I'm going to go on. The claim, and this I think some of you may have seen. What I'm about to say, I think some of you have seen, like last semester, but you just might not have seen it written with vector symbols. And to be as clear as I can be, yes, I am. We're now at the stage where, like, I ultimately do want to be precise about the vectors and all that. But I'll even admit, for today and for the next couple of days, if your biggest concern, if you can, and especially since everybody is stressed out and stuff, go big picture and triage with me for a minute if desired. Like the big points that I'm going to try to make today are really more about magnitude than they are about direction. If you could just follow what I'm saying about big picture, about sizes, the direction will be obvious to you. It's just that what might not be obvious is how the direction gets converted into symbols and notation, but that's not maybe that's not the primary concern today. I mean, I guess we'll see. But all right, so here's the law. The law of gravity. The law is that if you ever have any two masses, mass one and mass one is automatically going to exert a force onto mass two. It's going to it's going to pull or push it. And I think we're talking about gravity. It's going to pull it. Mass one is going to automatically yank on mass two. In a direction that is ultimately toward mass one. I guess I'll get to that in a minute. But with a strength, with a number of newtons that is computed by all the terms in the parentheses here, like in this equation. This equation is from here on in the law of universal gravity. It tells you how hard any one given mass pulls on any other given mass. So what I'm trying to say there is the R with the hat over it tells you something about direction. Put that aside in your mind for a moment if you want. Look inside the parentheses. The parentheses is about magnitude. What the parentheses say are you take the mass of one, you multiply by the mass of two. So like literally kilograms by kilograms. And I will do a numerical example in a second on the next page. But you take a number of kilograms, you multiply by a number of kilograms, you then divide by the square of the distance between them. Now, I'm not saying this is obvious. I'm just saying, and I'm just saying it's true. R in the denominator, the white letter R in the denominator, notice it does not have any symbol above it at all. It doesn't have a caret. It doesn't have an arrow. It is just literally R. That literally just means the size of the displacement between the two. It means the distance, regular old number of meters between the two objects, M1 and M2. So what the law says is you take the size of one, the mass of one, you multiply by the mass of the other, you divide by the square of the distance between the two. So then you're going to so far have a number that's in kilograms times kilograms divided by meters squared, right? You're going to have this big number. But then you take that big number and you multiply it by what is known as the universal gravitational constant, capital G. It is a universal constant, much like Planck's constant or something like that. It's a number that you don't have to memorize, but it is always the same number. It's down here in red, and it happens to be a tiny number, 6.67 times 10 to the negative 11th is what it is always. So you take your kilograms, you multiply by kilograms, you divide by the square of meters, and then you multiply by this 6.67 times 10 to the negative 11. And then you multiply by these crazy looking units afterwards. Like, okay, I see something's in the chat. Just 1 second. This universal constant, which I'm asking you to know about, and I'm asking you to know it's always the same number. I'm not asking you to commit the number to memory, although if you do enough of these problems, you automatically accidentally will. But notice the units of the number. They look obscure at first. Newtons times meters squared divided by kilograms squared. Like what? But the purpose of the units is to land the plane that I was just saying a minute ago. In other words, until you plug that number in, you've got a bunch of kilograms times a bunch of kilograms divided by a bunch of square meters. But then you multiply by this number that's measured in newtons times meters squared divided by kilograms squared. So the meters squared will cancel out. The kilogram squared will cancel out. That's on purpose. And what you're left with is a number measured in newtons. You'll be left with a force. I'm going to get the chat in a second, and I'm going to do the numerical example in a second. But what I want to say conceptual or, big picture to you right now is, and this is a law. I am not pretending to prove this right now. It really sort of can't be proven as such. I mean, it's a law. I'm not pretending to prove it. And I'm also definitely not pretending to say, doesn't this make obvious sense? Like, wouldn't you expect that the world would work this way? I'm not saying that at all. Not at all. I'm not saying that you would expect the world to work this way or that at the moment there's any self-evident reason why the world should work this way. What I'm saying is, in the manner of Newton, it's a discovery that apparently the world does seem to work this way, that things pull on other things with an amount that is directly proportional to how big they are, but inversely proportional to the square of how far apart they are. I mean, on a very intuitive level, it might not be as shocking that we're saying bigger things pull harder on other bigger things, and closer things pull harder on closer things than they do on farther away things. I mean, that's in English what it's saying. But why exactly the distance between the two objects gets squared, we have to eventually get to. Right now, I'm just saying that apparently it works. Apparently it's true. Last, and then I will pause and I'll look in the chat and I'll do the numerical example. But I'm saying that big number G, without the big number G, we're just saying in English, we're just saying big things pull on we're saying big things that are close to each other pull on each other a lot. And small things that are farther away from each other pull on each other less. That's all we're saying until the big G gets introduced. The big G, you might say, but what's all with the big G? The big G wouldn't even have to be there if we didn't already have an agreement that we want to measure the world in SI units, in MKS units. Like honestly, the point is we already do physics even before this law comes along. We already have meters, kilograms, and seconds, and we have idea of force is already measured, like F net already equals MA. So force is already measured in units that we call newtons. But what's a newton of force? A newton of force is a kilogram of mass times a meter per second squared of acceleration, right? Newton's second law, F net equals ma. So a newton of force is already a kilogram times a meter per second squared. So this big G number that's in there is actually just a scaling factor that just adjusts everything and adjusts the sizes and the units, the dimensionality, so that the answer that this whole relationship spits out is a number of newtons. If we weren't already, in other words, it doesn't change the concept at all. It just adjusts everything so that we're staying in a consistent system of measurement. That's its significance. So it just needs to be that number so everything works out in our system of measurement. If we wanted to switch to a different system or something, we could just set G equal to 1 and we conceptually would still be fine. Everything would just be scaled differently. So That number is 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. It's the constant of proportionality that you multiply the masses by, and then you divide the square of the distance by. And at the end, what is spat out is the force of gravity that any one mass called mass number one will exert on any other mass, call it mass number two. That equation gives you the magnitude of the force exerted by one onto two. Oh, and last, I'm totally getting a chat. I haven't forgotten. But what also might be sort of still confusing people or whatever, part of the discussion I was just saying a minute ago, R hat, R with the caret above it, that is a unit vector. Now, even if you're still a little foggy or nervous about that, the one thing I can say about unit vectors always, every unit vector always by definition has a size of 1. So whatever that R hat is doing in this equation, it's not changing the numbers. Like when you're done multiplying everything in the parentheses, you then in effect you multiply it by 1 if you're trying to pay attention to that unit vector. So whatever you're thinking about that unit vector, it's all about all it's telling us is something about direction. It does not change anything I was just saying about numbers or size or quantity. Now, wait, I'm going to pause for a second because I know there's at least one thing in the chat. Hang on. Oh, okay. I'm looking. Yeah, 100%. All right, I'm going to read this out loud. I'm not going to read the person's name, but like this, thank you. This makes me feel a little bit better, actually. Someone saying, I'm sort of paraphrasing, but to understand this for me conceptually, is it sort of like this example that I am M1 and I pull someone on the other end of a string M2? So I multiply by the universal gravitational constant. Oh, and using that, you divide by the distance between the two of you squared, the R squared. Okay, so I'm really glad for this question, and the person should give themselves points. The more carefully I'm reading it, the more I guess I see what the value of this question is. Like there's a lot that's, at first I thought it was 100% correct. There's a little bit that might not be 100% correct that I'm going to address right now that might clarify things for other people. The person's asking, is it a little bit like if I were on one side of a room and pulling on you, and you're on the other side of the room and I'm pulling on you like with a string? And this law is like giving like how hard I would be pulling on that string, I think is what the chat is saying. And yes, it's like that, but here, that's a good starting analogy. But here's like the big point I'm making is that what this law is telling you, and again, this is not a sidebar now, what I'm about to say. I'm addressing the question, but the question is helping me make the real point that I want to make to everyone. It's on the topic. What this law is saying is that the minute I exist on one side of a room, and the minute you or any piece of me exists on one side of a room, and the minute any piece of you exists on another side of a room, or the minute a piece of the sun exists somewhere in outer space, and the minute and a piece of the earth exists in outer space, what we're saying is that I don't have to touch you with a string to exert a gravitational pull on you. And the sun does not have to touch the earth with a string in order to exert a gravitational pull on it. And I don't mean this sarcastically or critically. The depth, the profundity of this law is it's saying there's automatically a phenomenon called gravity that exists between and among all pieces of mass in the world. Automatically, the minute a piece of mass exists, it acts as though it has like an invisible string that is attached to any and every other bit of mass in the universe, and then yanks on that string with a certain number of newtons in the way that strings can do that. But what we're saying here, and this is a big deal, like I'm yelling, like it's a good question for this reason, and it is a surprise. We're saying apparently everything acts as though it's on strings, but it doesn't need any strings in order to do this. You don't have to do any kind of activity at all. You don't have to move. You don't have to touch in order to exert gravity, in order to pull on other things gravitationally. All you have to do is be a mass. All you have to do is exist. Now, again, I am not yelling at that. I am yelling because I'm like, but I'm saying this is what is interesting and universal and surprising, possibly even confusing about gravity, is we're saying gravity acts like a string, but there ain't no string. Like there isn't actually a physical material piece of string. So we're saying this law tells you how to calculate the force that ought. Well, here's the example on the next page. Well, yeah, here's the example. I'm just looking what. Yeah. Here's the example on the next page to make it concrete. I'm saying if you literally have a 25 kilogram mass over here and you have a 2 kilogram mass over here, they don't have to be doing anything at all. Or they could be doing things and it doesn't matter. They're just sitting around and they're separated by a distance of 5 meters, right? We're saying, well, there's a bunch of things in yellow that I'm saying in a second, but we're saying if you just automatically, if you just plug those numbers into this equation, you just plug the 25 over here, 25 kilograms, multiply by the 2 kilograms over there, and then divide by the 5 meters squared. So 25 square meters, if you like. If you do 25 times 2 divided by 25, and then take that result and multiply by 6.67 times 10 to the negative 11th, you'll get a number like in yellow, like 1.33 times 10 to the negative 10th. That's the number you'll get. But also if you look at the units carefully, you'll see that the kilogram squared from the mass and the mass up in the numerator will cancel out with the kilogram squared that is built into the denominator of the gravitational constant. And you'll see that the meters squared down below, the 25 meters squared, will cancel out with the meter squared that's built into the numerator of the gravitational constant. And all that will be left over is the one other unit that is part of the gravitational constant, and that is newtons. So what you're left over with is this force of 1.33 times 10 to the negative 10th newtons. And what we're saying, and I am saying this again, this you could see there's a slide for it. So obviously this was like my point anyway. It's not just about one person. I'm saying that just if you just sit around and you have any number of kilograms at all, which everything does, you automatically will exert a force. Like you'll automatically pull. So back to the person's example, if I'm sitting around in the classroom, 5 meters away from you, then I'm automatically pulling on you by, say, this amount. I'm also pulling on your neighbor by this amount. Now, and yes, if you're following me, I'm saying if nothing else were happening in the universe at all, if you were, for example, happening to be sitting on a floor that has friction between it and your feet, you'd come flying toward me. But the fact is, there's lots of other things happening in the universe, such as the fact that you're on a floor that's exerting friction onto your feet, and the friction happens to be strong enough to hold you there on the floor. Also, I might add, I'm not the only thing pulling on you gravitationally. There's also, for example, like a wall behind you that's pulling you in the other direction gravitationally. I'm saying this is happening all the time among all pairs of masses in the whole universe. If nothing else were ever going on at all, everything would crunch together according to gravity. But there are other things going on in the universe as well. But this is the gravity. So, okay, last, and I'll take a breath for a second. What I'm saying is automatically everything is exerting a pulling force on everything else, and everything's doing it through empty space. Everything is exerting a pulling force of newtons on everything else in space, which means that everything is creating some kind of F that then gets plugged into the left side of Newton's second law, F net equals ma. right? But here's one little why I got like all stressy like a month ago during homework 1B, homework 1A, about like that Newton's second law is not F equals ma. Newton's second law is F net equals ma, or the sum of the forces equal ma, meaning that an object accelerates due to the sum of all forces acting on it, like always. So this gravity that I'm talking about right now is the calculation or the law for one force that's acting on anything and everything at all times. But other forces are also acting on objects. So objects accelerate or don't as the result of all the forces acting on them. Right now, I'm just talking about one called gravity. And but I'm saying this gravity is always there. And bottom line, I'm saying I hopefully to answer the person's question, and then I'll look in the chat again. I am saying that this is a sort of a surprise. Like I didn't know that life was going to be like this, but evidently, unlike other forces that you're familiar with, unlike tension in a string, or unlike friction from a surface or normal force from a surface, this force gravity, one of the reasons we call it universal is that it doesn't require any activity or material contact for it to occur. In fact, honestly, that's really the reason I call it unthingy. I'm going to say a lot more about that. But the point is, gravity just acts through empty space, apparently, automatically, which is also why people didn't necessarily know about it or believe in it until the mid 18th century. Like, it's not obvious that the world would be this way, but apparently the world is this way. Okay, wait, I'm going to pause for a second. I'm looking in the chat. Hold on. Right. Oh, wait. So in the chat, so in the public chat, I see tree. I appreciate it. And yes, and again, and by the way, again, if R hat is important, obviously I wouldn't put it there if it weren't important, but it may not. But if it's the detail that's confusing anybody, you could put it to your side for it may not be the most important detail right now. But yes, but what tree is saying about the R hat is correct. It literally is like a direction. It's literally just saying the direction of the force. I'm going to be more specific about that in a moment. But it does affect the math, as in it affects the equations and the results, but it doesn't affect the numbers. I will tell you exactly what it's doing to the results like in a moment. But yes, R hat is there to specify a specific direction. So yes, to tree's public question. All right, so wait, so I'm still looking in the chat. Hold on. Okay. Huh. I mean, there's an interesting analogy in the direct chat, like a different like another person, an interesting analogy about calling it like a gravitational blanket, where like things are put in the blanket and then the blanket sort of dips around those things. And that's a great analogy, and I'm familiar with that analogy, or like a trampoline. Like that's a fantastic analogy in many ways. But to be honest, that analogy, I'm not saying it's wrong. I mean, it's very, very right. But that analogy is helpful if you're trying to understand gravity in a really modern way, like in an Einstein general relativity way. If you want to think about those things, like I'm all for it, I love it, but I'm not even saying anything that deep right now. I'm just saying that everything pulls. So I'm saying maybe more a slight analogy. It's like I'm saying the whole world is in a net in a way, that there's invisible strings tying us all together in a way, is kind of what I'm saying right now. But yeah, I love the trampoline thing. I know the trampoline thing. That's awesome. But it might okay. Okay. And then I see something else in the chat that's thanking me for that. Okay, cool. Okay. I'm looking at the top. All right. And again, the main at least at the beginning of the homework. Well, all right, I'm just gonna keep going. Hold on. I'm just making sure I didn't skip anything. So this page That is, M1 will exert a force vector onto M2, right? That's what I'm saying. This force vector will have magnitude and direction given by the above equation, right? And the equation is the one where I just did the example. But now, okay, I'm going to say a little bit more about this unit vector thing. Bear with me for a second. It may really clarify for some people, or it may make it worse for some people. Just like listen with an open mind. Because the point is that force is a vector. It has magnitude and direction. And directions mean things like south, north, east, west, etc., or at angles. But when we're just dealing with two objects, the key direction, like you can almost think of it as we align our coordinate, kind of like with the inclined plane and all that stuff. You can think of it as we take our coordinate axes and we take the origin of our coordinate system, we sort of place it at one of the objects. And then in our minds, and then kind of align the x-axis so that the axis points directly to the other object. Like the most relevant direction of all is in a situation that we're talking about here, the most relevant direction would be the direction that points from one object to the other, right? So the direction of r hat, what r hat is designating is literally that, is the direction along the line, the straight line connecting M1 to M2. So I'm going to say it again. So r hat is not necessarily north. It's not necessarily east. And in fact, specifically, if nothing else is going on besides these two objects, we might not really care that much about north or east. What we care is the line connecting, the imaginary line connecting the two objects. So r hat, so the way you think of this is you got M1 over here, you got M2 over there, and in your mind, you draw a little arrow of length 1 that specifically points from M1 to M2. That little arrow is called the unit vector for r hat. It's got a direction that points from M1 to M2, and it's got a length of 1. So you think of that little arrow in the equation. You think of that little arrow, r hat, yeah, the white r with the caret over it, right? And then what everything in the parentheses tells you to do is it tells you to multiply a bunch of numbers together and divide by, r squared and get this whole big new number that's measured in, you get this whole new number and you multiply r hat by that big number. In other words, you take this unit vector of 1 and you stretch it by a certain amount, or often you shrink it by a certain amount. And now it's a new arrow of a different size. And now, because you multiply by all those numbers, not only is it a different size, but now it's an arrow that is measured in newtons, not in meters anymore. So now you've taken this old arrow of 1 meter length that's pointing in a certain direction, and you've scaled it and turned it into a force vector of a different size and a different measurement in newtons, right? So now you got a certain number of newtons that's pointing from M1 to M2, right? That's its direction, like from M1 to M2. And then there's a negative sign before the whole thing. Notice, and this is what I'm now saying that I didn't say anything about yet. There's a negative sign before the whole thing. And it's always there. In the gravity equation, the negative sign is always there. What does the negative sign do? The negative sign says, okay, now take that arrow, that force arrow that you just built. You started with a 1 meter displacement arrow, then you scaled it and you converted the units. So now you've got this, in the case of this example, you've now got this like 1.33 times 10 to the negative 10 newtons arrow that's pointing from M1 to M2. And the negative sign says flip it, rotate it 180 degrees, and point it, therefore, back at M1. Why? Because at the end of the day, what the force is saying, what the force vector is now saying is, if you have M1 over here and you've got M2 over there, M1 will exert a force of magnitude 1.33 times 10 to the negative 10 newtons, and a direction that is pointing back onto M1, the force that M1 exerts onto M2, the direction of that force is pointing toward M1 necessarily, because of that negative sign, flipped the R hat vector. The R hat vector said, look over there at M2. Then the negative sign says, flip your gaze and look back onto M1. Why? Because gravity is always a pull. The negative sign combined with the R hat ensures that the direction of the, so in the end of the day, and this is partly to get to like Tree and other people in the chat, at the end of the day, what am I really saying about direction? At the end of the day, I'm really saying something that you already totally knew. It's not new information and it's not hard. I'm just trying to show you how the notation, the math captures what you already knew. I'm saying that by using R hat in the equation and a negative sign, that is a way of answering the question, what is the direction of the gravitational force? And the answer isn't necessarily east or north or anything like that, or the answer of the direction of the gravitational force exerted by M1 onto M2 is pulling is directed toward M1, i.e., it's a pull, not a push. That's all what I'm saying, honestly. And I'm going to look in the chat in a second, but then I really do have to move on. The negative times R hat is the mathematical way of saying that M1 will yank M2 toward it. Gravitation is always an attraction, not a push away, a pull toward. That's what the negative sign. If the negative sign weren't there, then this whole thing would be M1 pushing M2 away from it. But with the negative sign there, it's M1 pulling M2 toward it, which is what gravity always does. That's all the direction means. It's not east or north or west, it's toward. Okay, wait, yeah. And it is an invert. I'm looking at the chat. Okay, well, wait. Okay, wait, now, what someone in the chat is saying, what about like if we looked at M2? That's what this page is. And I do have to go on and say, this is now a force, and all forces obey all of Newton's laws in all traditional respects, including Newton's third law. So if we looked at this from the point of view of M2, if we look at it from the other, then M2, then if we looked at it from the point of view of the other mass, then we would draw an R hat vector pointing from the other mass toward M1. Like R hat points from the mass that you're looking at toward the other mass. So then you do all the same math and everything, and M2 creates a force that would be pointing toward M1, except there's a negative sign there, so it flips it. So M2 is pulling M1 toward itself. In other words, to answer the chat question, I'm saying who's ever looking at the situation will always find that the direction of the force is negative, because negative means toward the looker. It means pull. That's what I'm so the objective direction. So whatever I do to you, you do to me, but in the opposite direction. It's just so what I'm saying is, whatever you regard as the mass that's creating the force, like M1 is pulling on M2, the sun is pulling on the earth, but automatically, necessarily, according to Newton's third law, the earth is also pulling on the sun, necessarily. So whichever you're looking at a given moment is up to you. But whichever one you're looking at as the cause of the force, we call the source. And generally, we make that the big letter, the capital letter with the number 1. I mean, that's a convention. But whichever one you're looking at as causing the force at that moment, that's called the source mass. And whichever one is receiving it, you call the test mass. That's just, okay. Okay. So, right. I think I agree with the person in the chat. I think I'm going to move, and I'm watching that we have 11 minutes. So I'm going to, now and look, again, I feel a little frustrated with myself at the moment, because I think most of you actually, I think it's simpler than, I'm like yelling and we're getting like sort of in the weeds, but like It's what you think, I think most of you, okay? The big punchline here is how we're using the negative and the unit vector notation in order to capture the intuitive reality that gravity is always a pull. The takeaway is anytime you see a negative sign in a force of this kind, it means pull. It means attraction. Now, the reason I did all this gravity stuff, we have 10 minutes. The reason I did all this gravity stuff is that you can sort of picture masses. They're big, they're macroscopic, and you've heard of them. And you can picture bricks and brick houses, and you can picture Earth and moon and sun, sort of. The two things about this law of gravity that you need to take away and bring into the rest of the discussion is that, first of all, gravity is action at a distance. Like I was sort of saying to the chat person a second ago, I mean, to all of you, it's action at a distance, meaning it's entirely unthingy. No touching is necessary for gravity to happen. That's interesting. Most other forces we've ever encountered don't seem to be like that. But it just is what it is for the moment. So it's action at a distance. Gravity transmits through empty space. But the other thing to know is got this inverse R squared proportionality, like that gravity acts through empty space, but the amount of space matters. The greater the square of the space between two objects, the less the gravity. It's inversely proportional to the square of the distance. I want you to notice those two things about gravity, that it's action at a distance and that it's inverse R squared, because the main thing that we really have to look at here for the next 9 minutes and the next several weeks is apparently electricity works the same way. I mean, it's a little bit harder to picture because it's microscopic, but that's why we start with the macroscopic example of gravity. According to Coulomb, the 19th century physicist, any two bits of charge, call them Q1 and Q2, separated by a displacement R, they will interact with each other according to the same type of mechanism, the same type of phenomenon as gravity. This phenomenon is called the electrostatic force. The one, and you know what our charge is, like an inherent property of matter, of thingy things, just like mass is, only not all matter has mass. Some matter does not have charge. What matter has charge? Protons and electrons. The proton is like the fundamental bit of positive charge. The electron is the fundamental bit of negative charge. And I don't know why charge exists. Just evidently it does. But the one, and we're saying the way charges pull or push on each other, apparently is going to work, works through empty space, just like gravity, and apparently is going to work by math that looks just like the math of gravity. The only catch is, as you know from chemistry and high school, etc., charge comes in two varieties, what we call positive and what we call negative. So protons and electrons. So we're going to take that. So in other words, apparently charges can pull on one another, but they can also push, which is in fact one of the main reasons that the universe is stable, why we don't all come crunching in on one another from gravity, because there isn't only gravity holding everything together, there's also electricity holding everything apart in the universe. So how does it do that? Mathematically, by an equation that looks just like the gravity equation. Only a couple things to notice. Number one, there's no negative sign automatically in the equation anymore. The equation comes out either positive or negative. You'll see how and why in a moment, depending on the charges. So the equation just comes out the way it comes out. That's number one. Number two, it's not masses anymore. It's charges, Q1 and Q2. Charges are not measured, charge amounts are not measured in kilograms. They're measured in units that we call coulombs, after this French guy, Auguste de Coulomb. So it's now coulombs rather than kilograms. And then the whole equation gets multiplied by a universal constant, just like gravity did, only it's a different constant. It's K sub E, like electrical constant is one way of writing it. And that's a different number measured in different units. Again, I just want to reemphasize, I'm going a little faster now because we only have 5 minutes. And this is what the board meeting in the lab, whether it's this week or next week, will be about. And this is what the homework is about electricity, not about gravity. But whenever you're having difficulty picturing electricity, try picturing gravity and see if that helps. We're saying the two main same things. It's action at a distance again, and it's again an inverse r squared mathematical equation. The adjustments we have to make to get to electricity are, number one, the constant is now different. G was this tiny, tiny number measured in newtons meters squared divided by kilograms squared. This one is a huge number, 8.99 times 10 to the ninth, measured in newtons meters squared divided by Coulomb squared, because Coulomb is the unit of charge. Okay, what is a Coulomb? A Coulomb actually is a very, very large amount of charge, actually, because of the way history evolves. Coulombs come in packages known as protons and electrons. But protons and electrons are very tiny in size, and in fact, they're very tiny in the amount of coulombs that they represent. In fact, one proton is approximately positive 1.60 times 10 to the negative 19th coulombs. It's a tiny number of coulombs as a proton. The electron is the same number of coulombs, but negative. Now, this is a tiny amount of coulombs. So if from now on, if I say there's a point, or like in the homework or in the board meeting, if we say there's a point charge of 1 positive coulomb over here, what you could picture that as like a proton sitting there, but it really isn't one proton. If we say 1 coulomb, that's actually a lot of protons all jammed together into a tiny space. In fact, given these numbers, if I say 1 coulomb of positive charges over here, that really means about 16 quintillion protons jammed together into a tiny space. A little bit harder to picture, but is still the case. But which is why if you get into trouble, try picturing gravity and masses instead. But if you have a coulomb of positive charge over here, and you have a coulomb of negative charge over there, they attract each other in the same way that masses gravitationally attract each other. One thing to note is that the mass is that protons and electrons, they have charge. They also have mass. The electron has a mass, very tiny, but it's measurable. And the proton has a mass that's actually like 10,000 times bigger than the mass of an electron, but still in the grand scheme, fairly small. So when protons and electrons are sitting around, they exert gravity as well as electricity. But if you run all the numbers and keep everything equal, like, if you have 2 electrons sitting apart from one another by a meter, they're each going to pull on each other gravitationally, but they're going to push on each other electrically. The electrical push is like 40 orders of magnitude stronger than the gravitational pull. I'm just saying, like, if you just run the numbers, the electrostatic phenomenon is much more powerful than the gravitational one. The gravitational one starts mattering once you have masses that are really, really big, like planets, and electrically neutral, like have the same number of protons as they do electrons. Okay, so we're dealing with now electricity. Okay, wait, hold on. Yes, that totally makes sense, what she's saying in the chat. I'm going to keep going because we have 2 minutes, but yes, that's totally helpful. One last thing to say, and then we're good for today, and you'll be good. Well, 2 last things. One with 2 minutes. This is our 3rd K in the class. Just the way physics is, it's annoying but true. Like, we already had a K for Hooke's law. We also had a K for angular wave number, 2 different Ks. Now we have a 3rd K. I'll generally write an E subscript at the bottom to show you that I mean this K, but you should also know for other reasons as well, it turns out in physics to be much more convenient ultimately to write K as a combination of other numbers. You'll see it looks messy at first, but it becomes more convenient to write it as 1 over 4 times pi times this other number called epsilon naught. You don't have to memorize it. You just have to be aware that this epsilon naught number is a tiny number. When you multiply it by pi, multiply it by 4, and then put it under 1, it gives you 8.99 times 10 to the ninth. So if you ever see 1, and you will, 1 over 4 pi epsilon naught, that whole package means the same thing as K. It looks more complicated now, but it ultimately simplifies things. So that's a different way that the same equation is written. Lastly, it's 10:40. There's the last thing I'm going to say. Notice positive times a positive always equals a positive. Negative times a negative always equals a positive. So if the two charges are of the same kind, you just put their signs into the equation. If the two charges are the same kind, the whole equation is going to make a positive answer. Positive means push away. If the two charges are different, it'll give a negative answer. Then it'll be pull, like gravity. No, KE, that's not kinetic energy. Totally a different KE. That's why I'm saying it's more convenient to write it. It's not kinetic energy. It's a different K. But okay. All right. But that's so bottom line. Okay. No problem. Bottom line, from now on, negative means pull, attraction. Positive means push. But that's literally the end. That's what you need for today. So you've been very patient and very good. Good luck with the rest of the exams. Best of strength. I look forward to them Thursday. I'll see you Thursday. Go fight, win. Got it. Okay. Have a good day. Yes, have a good one. All of you. Thanks. I'm stopping the record.